All right, I think that means we're live, so good morning, everybody. Morning. So it's an interesting setup here because you guys are all sitting on the edges and very few people in the middle, so if I look like I'm off the... So if I'm ignoring half of you, I'll try to change it up as we go along. Anyway, my name's John Howe. I'm a professor at MIT. I'm in the aeronautics department, which is perhaps for some of you a strange place to be hearing about AI. But we have a fairly large number of faculty in the department that work in the autonomy area, and I'm somewhat vehicle agnostic. I work in space, and I'll show you a little bit of my history on the next slide, but I've worked basically on ground, air, and even some underwater vehicles as well. So anyway, I'm going to talk to you today about reinforcement learning for robotics. It's a pretty generic title. Our work focuses a lot on multi-agent systems. You'll see me talk about that. But I tried to set up slides to give you a sense of the challenges in the area. What are the questions we're trying to answer? Give you a sense of the questions and issues. If anything, this talk should make you have more questions at the end than answers. And if that's the case, then I've probably succeeded. But I've set the talk up also to give you time to ask questions. And so hopefully at the end we'll have a Q&A, and if I get through these slides fast enough, and then we can have a chance to talk through perhaps a little more detail. There's no equations, try to keep everything pretty clean. As you can imagine, a professor at MIT, I'm used to giving these detailed talks to people experts in the field. I overheard a conversation down here about hyperparameters, so it looks like we have some experts. That's good, but I didn't want to assume that everybody was on exactly the same page. So if it seems like it's too high level, just get up there and ask me a question at the end, and let's dig deep down. I realize now that my email's not on the first slide here. It's on all the other slides, I think. It's pretty easy, though. It's just jhowe at MIT. It's about as short as you can get and still be legit. There's a .edu at the end, but it's right. Anyway, so let's get started. So a little bit of history about me. I was sort of recommended to give you some insights on the things that I've done. Again, we're talking more about robotics at the end, but this is actually from my postdoc work. This is, and again, dating me, but back in the 90s. This is actually a video shot by NASA in the mid-deck of the space shuttle. And for those that remember what the space shuttle looked like, there was actually where the crew sat at the top, and then the mid-deck was actually an experimental area. And this piece of equipment was designed to test vibration control. We tested it on the ground, we tested it in space, and this is the astronaut Steve Oswald actually doing the experiments for us. The super cool part about it was we were actually on the ground interacting with him. We did that for about 15 days, moving data back and forth. So that was just super cool. It got me very interested in space. This is sort of the culmination of a bunch of work in space for me. I then moved to Stanford, still interested in space. This is back when people were interested in doing space science with distributed satellites. So the picture on the left gives you an indication of sort of the type of distributed formation we were thinking about building. And originally the title was Orion. It's like Orion's belt, 3 satellites. Budget cuts happened, and eventually it became 1. So it wasn't much of a formation flying experiment, but we actually did build something. But this is back in the day when microsats and nanosats and the CubeSats that you hear people talking about now were actually still hard. And part of the challenge was actually getting enough propulsion on board that we can actually do something. These are the tanks that firemen use. Those are the only things that we could get approved to actually fly. Sorry, I'll try to point on both sides here. That's the tank right there. So everything was scaled by basically that. But you can see some of the electronics sitting next to it, and it's kind of laughable nowadays. This is in the mid-90s. Everything on that board now would probably fit on your thumbnail, but that's the way that things go, right? But the thing you can't change is the amount of solar panels you need, and that basically ended up sizing this thing, which is about a ½ meter cube. Super frustrated with the fact that you can work on things for about 15 years for going into space and then nothing ever happens. I decided when I moved to MIT in 2000 to go back to work on UAVs. If you know the history of what was going on in the OO's time period, there's a lot of interest in the Air Force in working with multi-UAVs at that time. They look like specks, but these are the little airplanes. They're actually flying information up in space, up in the air. And what was cool about that, I think there's actually a date on that. It was 2003. And again, this is back when, I don't want to keep saying everything was hard back then, but think about flying autonomously with autopilots in 2003. Hard, right? It didn't exist. You basically had to, these were, like we had serial numbers 009 off for the autopilots. And we were working with the companies while we were in the field to have them fix the software on the autopilot while we were working with them. So the point is, being down this path in terms of multi-vehicle many times, done it with fixed wing, quad rotors flying around, done outdoor stuff, indoor stuff. This is sort of a motion capture lab that we have where we do a bunch of work when we can fly things around indoors. So that's all super cool. That gets me to about sort of 05, 06. I thought, this is about as cool as it's going to get. And then the Grand Challenge exercises started, right? And if those that remember the Grand Challenges, there was Grand Challenge 1, 2, and 3. We didn't get involved until Grand Challenge 3. This is our vehicle. It looks like it's going super fast. It's about 20 miles an hour. Just with the right camera shot, you can get enough blur that it looks like you're whizzing past. But it is, what the key part about that is there's nobody sitting in there. There's actually nobody in that thing. Of course, we're the other side of a concrete barrier, so we're pretty safe. But this is, again, back when people were trying to figure out how to do autonomous vehicles. And of course, the outcome of this urban challenge was what you now see of the self-driving vehicle activity. And the big tin can sitting on top here, that was $150,000 worth of sensing. That's the Velodyne that you see on almost every self-driving vehicle that exists now. It looks like a Kentucky Fried Chicken bucket. It's about that size if you've got the family meal. And basically, it's a spinning thing up there, and very, very expensive at that time, and only slightly cheaper now. And at that time, right, we would start creating pictures that look like this. I think this is a video that will run. This is 07, and at that time, you would rarely have seen a picture that looks like this. I don't think it's actually going to go, but this is us driving down on the bottom here with that thing. And all these lines are the different lines coming from that LiDAR. But we've got every sensor known to man. We've got vision, we've got radar, we've got single lasers, we've got multiple lasers from the LiDAR. And from all that, we're trying to infer everything that's going on around us. And you can see a huge amount of detail here. You've got buildings. You can actually, if you look carefully, you can actually see people in there. And so this is, again, back at that time was very cool. What, for me, this started doing, the reason I'm telling you all this is that I started thinking about control for very specific things. We build them, we fly them. Down here, I'm thinking about going to space still, doing multiple vehicles. But all this stuff was sort of inward focus. It's thinking about the vehicle. It's thinking about that entity and thinking about how to make it work better. When you start getting into the Grand Challenge, although this vehicle sort of looks like it's working on its own, of course it drove around in a competition with other vehicles, some human-driven, some manually, some other robots. And then you start thinking, and certainly I started thinking a lot more about, well, what's going on around me as a vehicle? It's much less of a problem of what is my issue, how do I drive, and much more about what is actually happening in the world. And so for me, this is really the recognition in terms of my background after about 15 years of research that the outside world was a whole lot more interesting than what was going on in the vehicle itself. And of course, if you followed the race, you will know that we had the first robot-robot collision. The other robots hit things, but they were stationary. We hit things that were moving. So we actually hit, this is Cornell on the left, this is us on the right. It's a long story. I actually wrote a journal paper on it to actually dissect the two data streams and figure out precisely how this happened. Long story short, basically, the Cornell vehicle was moving in a way that we had not really anticipated and when we were doing all the studying ahead of time. And we have perfectly good data, as indicated by this kind of stream up here. We knew what was in the world around us. What we didn't anticipate right at this instant was the fact that a stationary vehicle will start moving. And it seems rather self-explanatory at this point that, we had seen this vehicle, we've been following it, it would stop, start, but we didn't have a model of, we had a model of stationary things and we had a model of moving things. And the transition between the two was about 3 miles an hour. What we didn't have was a model of something that would stop and then move. And so what we had decided to do at this instant, well, just before this instant, was pass something which was now stationary. We were following it while it was moving. It stopped. We decided to pass it. We have a perfectly great maneuver for passing the stationary object, which then, of course, started moving again. And what was not included was enough of a reaction time for this thing to realize, well, now we're going to have a collision, so we did. Pretty mundane as collisions go. I mean, there was barely any body damage. I mean, if you've been driving this, you probably wouldn't even notice you touched it. Certainly in Boston. This is routine. So anyway, but from that, we, clearly, what I certainly extracted from this was an understanding of the fact that we need better models of what's going on in the world that are adaptable to the environment, that we can't just go in with a set of, first of all, fixed parameters on the difference between moving and stop. That's pretty obvious. but that needs to be adaptable as a parameter set. And the other thing is that we need to have dynamic models that are adaptable. We need to be able to capture other behavior in the environment. So we start from then on in the research group thinking about words like intent, we think about words like behaviors, and these are the kinds of activity that we're trying to capture. Now, if you fast forward about a decade, you'll get to here, and this is now us driving a robot. We actually have a laser on top that's about the same quality as the Velodyne. It's the little thing up there. It's about 2 orders of magnitude cheaper, but we're trying to show this as driving in a much more complicated environment. We're now sort of unleashed this is what we call the wild, right? We're in one of the buildings at MIT, and we're driving around these unsuspecting pedestrians. But built into this is a full understanding of the world, what these pedestrians are likely to do, how best to behave. But it isn't just a collision avoidance problem that this vehicle is trying to do, it's actually behave in a socially acceptable manner. One of the things you don't want to do as a robot is actually pinch a person into a corner and then sort of make them behave in a way that they're uncomfortable with. So there's a whole discussion about what makes something socially acceptable. Like I say, collision avoidance in this day and age is not that hard. You sort of see all the stuff around you, it's not a big deal. Predicting where it's going to go is a harder problem. Predicting how you should behave to avoid what you think it's going to do, that's when things start getting hard. That's where the challenges start happening in terms of the research itself for single vehicles. But as I said, we've started thinking, my group does a lot of research in multi-vehicle work, and you might recognize this challenge problem, which is, okay, so that's how you drive one robot around in a sort of pedestrian environment. What if you were part of a package delivery team and you had multiple robots, and I must apologize, our graphics group is not the best in the world, but it's a bunch of grad students who keep coming to you and saying, look, I can either write the paper or I can make good graphics, right? And I'm like, okay, so I want both done. Can you do them tonight? And this is what we get. So I apologize, but I think gets the message across. And so what we have is a team of robots here that are helping provide or do the package delivery in the neighborhood that we wouldn't necessarily have visited before and don't necessarily have a good map of the environment. And we're sort of just showing here cartoonishly sort of the picture from above, but you get a sense of those robots doing things. So now if you sort of show up as a robot, there's interesting questions that get embedded in statements that we as humans find quite easy, right? Like statements like deliver the package to the front door. I think it's relatively clear to all of us where the front door would be. It wouldn't be immediately obvious staring at this if you didn't know what the definition of a front door was. Is this the door? Is this the door? What's going on? I can't actually even see the door. Now, you can go through and map the world and sort of come up with a good description of this environment, but as you know, every house is going to end up looking slightly different. There are repeat customers who will be going back, but you'd like to be able to handle situations that are new and sort of innovative for those robots. So you have a robot show up, it's asking the question, how do I get there? And so there are some challenges it has to figure out, and that's when you start getting into the discussion of how might you go about solving this? And again, if you had a model and you had a map of the world, there probably isn't a huge reinforcement learning problem. If you start relaxing those assumptions and you don't have models of the world, you don't have that map, you end up with trying to answer the question using techniques like this. So let's just run through sort of exactly what this is. So we have the 2 happy robots at the bottom. They're trying to sort of work in this environment. And like I say, much of what I'm about to say on the next couple of slides sort of address the question of reinforcement learning. I'll talk then about some of the subtleties associated with multi-agent, which is slightly different and slightly more complicated, and you'll get a sense of what the differences are as we go along, okay? But I'm gonna mention some words on these slides that are key because I'll keep reusing them, and I wanna make sure we're clear on the nomenclature. So the notion here is that the robots are taking an action indicated by the symbol A, and I'm not going to use the symbols a whole lot, but it's just the words action. So we take an action. The action could be many things, right? It could be that you take a picture. It could be that you actually drive around and look at the hill from the other side. It could be that you actually move some of the trees around. There's a whole bunch of different things you could do. You take an action, you get and then the state is going to change, right? It's going to change from sort of S to S prime. So the subtlety here was the students actually show it. It's like we're looking at the world from the other direction. But something's changed, right? And the point is that now in that world, you're going to take some observations and you're actually going to see some things. And from all that, you're actually also going to extract a reward. And the notion of multi-agent, typically for an agent, there's just a reward. For multi-agent, there's a bunch of rewards. The premise in these multi-agent problems is the thing you're interested in is the sum of all the individual rewards. Okay, that's how you get the multi-agent reward. So this is sort of notionally shown as, as a sort of a reward taken for each of the agents, which is then given to both of them. They get the same reward function, okay? So those are the key statements. You've got states, you've got actions, observations, and reward. And from all that, what we're trying to extract then is essentially a policy, right? So a bunch of words at the bottom. The objective then is to learn a policy that then allows us to figure out what the joint actions should be based on maximizing, but the objective being to maximize the shared reward. So again, what is a policy? Let's make sure we're clear on that. It's essentially a giant lookup table, okay? The device showed up with a state and said, in this state, in this situation in the world, which includes you, what you're doing, what your friends are doing, what the world is doing, in that state, what is your recommended set of things to do? So think of a giant lookup table that goes from a giant state vector through this lookup table into a recommended set of actions, which in this case could just be two scalar numbers, A1 and A2, okay? And what we have to figure out is what is that giant reward, that giant policy, and the way we learn it is by by doing a bunch of training. The training then is going to go through the sequence of actions, observations, and rewards. You then sort of mentally are thinking, unless you're going to collect data, what is going to happen in the environment, how are things going to change, you get that reward, and then you say, was that reward good enough? If it is, then you sort of say, well, that was good, let's remember that action and that behavior, and if not, then you sort of chuck it out and think of a new one, okay? That learning process is exploration, right? You're basically exploring in the world. If you have information about it and you have a policy and you know what you're supposed to be doing, you do what's called exploitation, okay? And you'll often see a trade-off between exploration and exploitation, and it's about if you have information, you should exploit it. If you don't have information, you should be doing more exploration to obtain it. That trade-off is fundamental in what happens in RL. The challenge typically is you think you have good information and you're exploiting it. However, it turns out to be bad. You're exploiting bad information, which means you're just wandering around not accomplishing a whole lot and nowhere near efficient as you might be if you did more exploration. The problem with exploring is you're potentially wasting time looking for things to be doing when it turns out that you actually knew what the right answer was, okay? So the question ultimately ends up being, do you think or know that you have good information and can exploit it, or or not, in which case you need to be doing more exploring. So in the situation, say, of the robot here, the classic situation might be that I know perfectly well how to get to the front door in the case without the tree, and then our graphic artist had a tree fall down, the result being now this is different than I had before. Now, as a robot, the standard strategy for solving this problem would be, wow, the world is different than I was expecting, or this is just the way the world is. I don't have a good answer to this. So you essentially go to the lookup table and say, how do you get to the door when there's a tree in front of you? And the answer is, I don't actually know, in which case what you would then start doing is exploring, right? So you basically offer the world exploring, and you've probably seen robots explore like this before, and they're basically just wandering around looking for the edge of the tree, hoping to find a way to get around it, and then see whether or not they can actually get to the door in an efficient manner, right? But again, for delivery, right, you're interested in things like economy, right? I don't want a robot that's wandering around someone's front yard trying to get around trees, wasting time, because ultimately this is a package delivery problem. I'd like that it was done as quickly as I can. So the question is there a more efficient way to go about this? What one could imagine is basically posing the question to another robot that's sitting over here. Hey, have you ever experienced a situation like this before? Maybe there's a bunch of trees that are falling down this neighborhood. Have you figured out how to do this and get around it? And can you help me figure out how to do this in a more efficient manner? And then basically you get the question, what you were thinking of doing before was bad. This is the right answer. Go ahead and do it. Now, there's nothing saying that the first robot couldn't have figured this out on their own. The point is that you're trying to do it in an efficient manner. Efficiency here means number of samples, how much wandering around am I going to do in this exploration, and time, okay? And that if you could have a robot that ends up exploring the entire problem, but if someone else tells it what the answer is, of course, that ends up ultimately being a faster thing to do. So with the nomenclature that I'm describing here, you'd think of this person as the teacher, they have some advice to give. This person being the student, they were basically asking for that advice. They're posing the question, does anybody, you in particular, have an answer to this question on how it could be done? Ultimately, of course, there could be multiple teachers, there could be multiple students. You might be a student one minute and a teacher the next. There may be things you know. So in the standard or the more general sort of multi-agent problem, there isn't a student and a teacher. There is nominally going to be a group of agents. They have mixed knowledge, right? And it's basically a question then of how does one not just exchange knowledge about, hey, there's a tree here, but skills, right? There are things you've learned how to do. How do you actually go about exchanging the skills of the things you've learned and the skills that I've learned? Ultimately, the goal of this research isn't to sort of just have an agent tell us, hey, here's the entire answer, but imagine this robot had discovered part of the skill required. This robot had discovered sort of the rest of the skill required, and then you're sort of able to then fuse skills together. This is sort of the holy grail of the type of research that I'm describing here. Okay? So this is sort of posed the question, and now we're in a situation when this robot can sort of then, like I say, sort of successfully execute the path to there. So I've talked about this a little bit before, but basically the goal here then is to enable the AI, the artificial intelligence, to learn how to coordinate between the robots, and selectively share local information in a multi-agent system. And the information here, as I said, could be a map of the world, or it could actually be as generic as the type of skills I was just describing before, okay? So the word skill could mean a capability. It's something you actually figure out how to do, not just something you've actually learned about. Why do we want to do this? We want to accelerate the learning. And again, the notion is that if you were doing it on your own in the sort of baseline type operation, you probably could have figured it out, but it'd be a whole lot slower than if someone was able to tell you. Ultimately, that should improve the performance of the mission. So if you're thinking about this as a package delivery problem, it should be improving the quality of that package delivery system. And it'd be super nice to not have to rely on experts/oracles. A standard solution you often hear described for things like self-driving vehicles is I will just have a whole collection of people sitting in a building somewhere, and if my self-driving vehicle runs into a problem, I'll just do like OnStar, I'll phone home, and I'll say, here's the map of the world, can you drive me out of this, and then figure out what to do. Of course, in that case, the robot's not really learning anything, they're just sort of being shown the answer, they're effectively manually driving their way out of it. It also requires that you have that sort of group of people sitting there able to do it, and then hoping that they actually can. And so here we're actually hoping, or sort of aiming to generate a group of agents that can educate each other and become sort of smarter as a team by taking sort of partially learned knowledge across the team and actually sharing it as needed. Now there's a bunch of challenges. And so when you get into these kinds of questions, you have to answer things like what to share, right? So what is it you're actually exchanging between them? You have to be able to know when to ask for help. So what are the issues in terms of, when do I know that it's more efficient for me to ask for support as opposed to do the exploration? You also have to worry about network constraints. If we get 5G, that'll be less of an issue. But if you're stuck with 4G or 3G, it is an issue. You have to worry about bandwidth. But one thing, of course, that's super important, perhaps a little less so in the cooperative package delivery problem, is privacy concerns, which is dealing with what am I willing to share with you, right? And that there may be things that I'm not, as an agent, willing to say in terms of the level of detail. I might be able to give you the abstraction of what it is that I learned from everything I did, but I'm not just going to give you a data dump and says, well, this is what I learned and this is where I was when I learned it. That might be a level of detail I'm not comfortable giving you. However, I could tell you the abstract versions of that and work with it. And so there's a key question that's coming up in a lot of this work. Again, that tends to be possibly cooperative, but like cooperative in quotes, right? It's sort of privacy cooperative as opposed to just the full scale, I'll give you a full data dump. All right, so I'll give you a little bit more detail on what we're doing here. So it's really dry here. So in this cartoon, we have our happy robots, Robot I, Robot J. And there's a bunch of nomenclature here I'm going to run through. Remember we talked about the word policy, right? That giant lookup table, a bunch of stuff goes in, right, the state vector, and something comes out. And at the task level, what you have is a robot that normally is capable of doing something. So it's stuck in this world. Cartoon sort of is a discrete world like this. It's sitting here. It knows the state of the world. It has some idea what just happened. It turns on all its sensors, gets that information in, and it has a policy that it's sort of either learned or done offline, but basically has something. It can change, but it has something for now. And the result of that, it has an action, and it says, okay, well, this is what I'm going to do. This is what I'm recommending I should do. This guy over here is doing the same thing. Okay, so that's the baseline. That's sort of where we're sitting. But then we have these other things that are going to sit on top of that. And we're going to end up with the hierarchy of policies, right? There's more than just the execution. At the execution level, I'm just like, this is what I do. Above that, what we're going to introduce then is policies that start looking like the ask policy. This is normally the student saying, well, maybe maybe I'm not that happy with this, or I don't think that's a great policy for me, or action for me to be taking. Maybe I'm going to ask for some advice and see whether or not there's anybody out there that actually has a better suggestion on what it is that I should do. So that's written here in the nomenclature of the ask policy. And again, this is not assumed that you know how to do this, right? I mean, do you know how to be a good student? Do you actually know what's involved in asking and asking for the advice? When you would ask for advice, what advice are you asking for? And when you decide to execute locally versus go and ask for it remotely, the premise is that that isn't something that's going to be obvious. And I think we've all probably been to school and know that being a student requires you actually learn how to be a good student. It doesn't necessarily something that's obvious to everybody. So that would then be a request, which goes to something here we'll describe as the teacher, right? Is the person that actually then, within the team, might actually think that they have an answer. What they provide is then a piece of advice. But again, and I have a lot of experience on this side of things, not all people are good teachers, right? So the premise is not that we start off as agents knowing how to provide good advice, right? So the notion is that there's a policy that I would have. Again, this is it. I would learn, what I'm learning as a teacher is how to respond to the request for advice. What do I say? When do I, sometimes I could decide that I shouldn't provide that advice. Maybe there's pieces of advices that I should give and when I should give them, okay? But the notion is that I'm learning this as well as a teacher. That's providing information then that comes down here to the task level, providing them an advise action, okay? And the difference, the notion is that this is different than that. The robot then executes that advise piece of action, all right? And from that, the hope, right, is not just that agent I here is actually executing or just executing what I advise them to give as agent J, but also that they're learning something from this, right? And that's one of the crucial elements here is it's very easy to provide input that someone can just execute, but what you also want is something they can learn from. So one of the things you do have to think about hard here is what's actually going on right here. There's a vocabulary that's going on between these two exchanges. What to ask for, right? What are you asking? What is the question you actually ask? And then the response, what is the actual feedback? And I've written things here, and in the papers we write, and I can send you copies if you ask me for send an email about it. You know, we have been thinking about a specific nomenclature that happens right here. It's not the only one, there's many options, but you have to start thinking about those things I described earlier. You think about network constraints, how much information has been exchanged. You think about privacy constraints, what exactly has been said, what is the format of that data that's moving back and forth, how abstracted is it, how safe is it, how confident are you that that you're willing to exchange it? And that gets into the discussion of what's going right in here. Obviously, that's going to impact the two policies you're creating above, okay? But again, as I said earlier, the notion is that, as shown here, agent I is the student or the ask, and the teacher and agent J is the teacher, but that's not always the case. And so all of these agents would have both a teacher policy, an ask policy, and an execution policy, and that sometimes you're the teacher, sometimes you're the student, sometimes you're just doing stuff because you know what to do, okay? But again, the working assumption is that all of these are going to be learned and actually developed. You might, the task level, you may have a good prior, you may not have a very good prior on these, and these are things that we have to learn as agents how to execute. And if you're familiar with the architectures that people typically use, this ends up being a GANs network. So there actually ends up being two policies inside each of these boxes, both the adversary and the generative network. So there's actually 6 things that we're learning at the same time, if you've seen these type of architectures before, okay? So pretty complicated, even the picture itself looks fairly straightforward, all right? So what happens is something normally that looks like this. You will have a picture where this is the baseline, right? So normally what you would have is just a bunch of agents out there. They're doing task level, they do exploration. And so this is shown as the blue box, the very low level part of that architecture. And there's just agent I and agent J, they're both operating in this world. The part of the complexity, of course, when you have multiple agents is that the world, as I describe it, for agent I includes what agent J is doing. And one of the complexities here is that agent J hasn't yet figured out his policy yet, or their policy. And so agent I is trying to decide how they respond and create their policy. Meanwhile, agent J is trying to do the exact same thing. But you can imagine this leads to a sort of non-stationarity is the word we use to describe it, where in the world, as I think about it, say as agent I, that's actually changing because agent J is part of my world and they haven't settled down to what they're doing. So this is part of the reason why this ends up taking a while. The result can ultimately be that over time, you sort of have a learning iteration, things improve, and the joint value gets good, but it never gets particularly good. And so these agents sort of converge to answers, but they're never particularly good, not as good as you perhaps would like them to do, okay? So that's the baseline. What we're going to add on top of that then is the architecture I just described. So this is all, in the color-wise, the exact same thing I described before. So at the top you've got the teach, in the pink you have the ask, in the blue you have the execution, right? It's 3 pieces. And notionally what we're doing then is going to learn all three of them. You've probably seen these types of problems before, but we have three nested things you have to learn. You can't learn all this stuff at the same time. They're actually being learned on very different timescales, right? You can learn to execute on a much different timescale than you might learn to be a student or learn to be a teacher, right? So you actually have to try to separate these out. So we're gonna have two parts to the learning architecture. One is sort of phase one over here, where for a given, and they're sort of notionally here shown as being locked. So we lock the teach and student policies, and once those are frozen, you then just learn how to be a good executor, right? And so locked doesn't mean that, this means these aren't changing. They're still, you can still ask questions, you can still give advice, but the learning phase within the teaching and ask are frozen at that point. And now we're just trying to get these two things to converge, and hopefully we'll converge faster, ultimately, once we get good ask, teach policies, okay? So we freeze the teach and ask, and then try to improve the blue. Then what we do is basically for a given blue, and I'm not sure why it doesn't show up here, but the blue down here is supposed to be locked, and then the green and red are being iterated on. So these are being sort of iterated on now for a frozen set of blue, and then we could now at this point be improving the task, well, the sort of teacher and ask policies, okay? And the picture down here is trying to sort of help you understand the sort of the timescales in which things are going on. There's a learning iteration that's happening here, but this is thinking over a longer time scale. This tends to be thinking about sort of instantaneous stuff. It's like, this is the behavior now. So at the task level, in the blue boxes, you're sort of thinking about how did things happen right now, and how did things go? And that's sort of shown by the vertical blue bar. But on the teaching, you're thinking about perhaps how do things go over an entire history, an entire epoch, right? You have to think about a relatively long time scale. You don't want to be thinking at a teaching level about what happened right now, because you get a lot of noise in that data. And again, if anybody here who teaches knows, if you're thinking about your teaching policy, you've got to be thinking on the time scale of a semester. You can't be overreacting to what happened on a given day, okay? So, of course, in any sort of phase one, phase two iteration sequence like this, you need to have the big iteration bar, right? And so ultimately you're gonna have a feedback loop. And so this is now gonna iterate. And so we're going through cycles here where we are going to freeze the blue and the red, the green and the red, update the blue, then update the green and the red, and then iterate back and forth. And the result ultimately would be, as you cycle through that, is that notionally things are gonna get better at this level, they get better at this level. And it's sort of when you become a better teacher, you become a better executor, and because you're better at executing, you become a better teacher, and then things just continue to get better and better, okay? All right, so that sounds great. What are the challenges? And there are many, many challenges involved here. And I'm trying to figure out, this clock is going down, so I should speed up. So one of the challenges is representation. And in fact, if you, in the entire field of reinforcement learning, the representation problem shows up many, many times. It turns out that the entire conference on representation is the International Conference on Learning Representations. To give you a sense of how important this is in the field, the attendance in that conference has gone up by a factor of 20 in the past 8 years. So it's basically just skyrocketed to something that when it came from nothing to now one of the larger conferences in the field. They're not just answering questions like the ones here, but they're answering basic questions like, given all this data, in what format am I actually going to represent it in such a way that I as a robot or an agent could understand it, okay? So notionally, I've described pictures like this where we had discrete worlds, and in those discrete worlds, you're taking discrete actions. Like you can either take one step forward, one step back, you can take a step to the right, and if you were dancing, maybe that looks good. As a robot, that's not so great, right? You want to be able to operate in a continuous world where you can be doing a whole spectrum of actions, different speeds, different directionalities. So you'd like to be able to move into a continuous space. The difficulty is that people work in discrete worlds because, quite frankly, although there's a scaling problem, it's much easier to learn in those domain spaces, in part because there's a finite number of things you're going to be doing, and so the learning problem becomes much easier. So this is easier to work with. This is a better representation for real life, but it's harder. And if you're going to work in here, you need to have a representational tool that has the capability to represent the things you care about. And what do we care about here? What's those policies? I'm trying to find a representation tool for the policies. And this is where you get to the work that ultimately has been driving what we've been doing here is deep reinforcement learning. And there's ultimately this ends up being these convolutional neural nets, and I'm sure you've heard a lot about. There's a lot of mystique about these things, but let's try to brush that aside for a second and just think about what these things are. You have a technique that is generating these giant lookup tables. It's from a given state space to an output. You have this thing notionally in some giant space. It's just a function. It just maps one thing to another. And all I want to do essentially is curve fit that. I just want to come up with a representational tool that will give me a way of capturing what that function looks like so I can write it down into my computer, and then I just ask the computer that, just essentially have that thing act like a lookup table. And CNNs and deep reinforcement learning, for all the mystique about them, essentially all they are is curve fitting. They're just curve fitting this giant thing. I don't know what this thing looks like, I really don't care. I just want to be able to curve fit it so I can capture it and put it in my computer and then use it, okay? And that's what the CNNs are doing. And the particular thing that's nice about the deep reinforcement learning is that whenever you do curve fitting, you probably did this back in high school and college and things like that, you'll almost always start every curve fitting problem by saying, given these basis functions, you pick the weights and then you fit the curve and everything looks good. You do like a linear fit, your curve is a straight line. You fit a quadratic, you fit a cubic. We're fitting something here in n-dimensional space. I have no idea what it looks like. I have absolutely no idea what the basis function should be. And so you just stand around thinking that through that problem, of course, you just talk yourself to a standstill. What deep reinforcement does, and the secret sauce involved, is it does not require you know what the basis functions are ahead of time. It helps you figure them out as you're going along. And so put the two things together. I need to be able to curve fit this giant thing. I have no idea what the basis functions are. Deep learning helps me figure out how to do it. And then backpropagation is just the way things talk about the update the weights. You're done. That's in one paragraph is what the secret sauce is of deep learning, okay? And there's a lot of details and there's thousands of papers on what's going on, but every one you read is essentially just doing what I said, okay? And so that's what we're doing. We have all these policies that we need to capture. They're working in a continuous domain. We need to have a representational tool. If you're working in a discrete space, you don't have to worry about representation tools. You can figure those out pretty easily. They're quite easy to write down. They're large, but easy to write down. What you're missing in the continuous space is what those representational tools are, and that's why I use the deep learning techniques. That's what we're using and a bunch of other people use as well, okay? So hopefully that sort of brushes aside some of the mystique. It's cool and everything, but when you lift it up and look inside, it's just a curve fit, okay? So then you get into teacher credit assignment. One of the big problems here is whenever you're giving advice, is how do you know the value of the advice you give? I'm sure you've experienced this in your own, right? It's like, I give you advice, something happens, you'd like to claim credit for it. As a teacher, I'd love to claim credit for everything my students learn. Not always the case, right? Sometimes they actually learn stuff by going to Wikipedia, sometimes they actually learn stuff by talking to other people, sometimes they actually went to the library and read a book. That's very rare, but you know, can happen, right? So you have to be careful what you claim in terms of the credit, right? Part of what you have to do is to let things mull over. You can't just, you know, sort of impose or suggest something and instantaneously say, wow, they figured out the answer to the question that they asked me about, fantastic, I'm a great teacher, right? Because you get a very mixed message out of that. Because there what you're actually doing is giving them the answer. That's not learning, right? They asked a question about something they didn't know. The real question is, can they take the advice that you gave them, distill it into a better understanding of what to do? And of course, this is why we ask hard questions on the final exam, because what we're trying to figure out is what you actually learned, not whether or not you can regurgitate what it was that I told you during the semester, okay? So to figure all this out, we need to have the teacher reward function. So we need to actually figure out, how do I as a teacher actually figure out or assess whether or not things are going well? And there's a big table over here from one of our papers, and the words here are simply to help you understand that you don't need to know what all these things are, these acronyms. It's just to help you understand that we've looked at a bunch of them, because there's a lot of work on learning how to teach that's been done within the context of human teaching. Of course, here we're thinking about robot teaching. And so they've thought about many different types of reward functions that the teacher can use, and we looked at every one of them. The one we converged on was VEG, which is the value estimate gain. And I just sort of bolded the numbers here and indicate that we did substantially better using that. This is actually sort of our idea based on how badly the others were going. So this is sort of, when I talk about our technique, it ends up sort of being this one here. But the other thing you have to do is to figure out what I was just describing, which is how do you know whether or not the students have actually learned versus just regurgitating what it was that I told them. And so what we actually effectively are giving these robots is a test. And so we actually give them a piece of advice. They ask a question, we give them a piece of advice. That will hopefully make them do better on what they just asked us about. But then we also check and see whether or not they actually got smarter, right? And so we actually, in real time, are giving them a test which they also have to do, and then we're checking to see whether or not they are better at doing the types of problems that they asked about than they were at the beginning of this exercise. But all this is occurring in sort of effectively real time within the learning, and that's what all these words say in here. But the key part, the key aspect of this is gets into this, it's just a question of whether or not you're giving one piece of advice, multiple pieces of advice. But here we're trying to embed a time scale, a length scale into the teaching and learning aspect that is in sort of the new work we're doing. But there is a question here about instability. You can have a situation where the learning, the feedback, you can have a great reward function, but the feedback is taken on such a short time scale that you end up with a lot of noise in that feedback. And that you as a teacher then get overwhelmed by noise and you actually end up learning effectively the wrong thing. You're taking the wrong message out of this. And so you have to be careful there. The other one, we talked about this a little bit, communication. But again, there are numerous ways you can do this. I'm talking about in the context of posing questions in terms of asking advice on what actions to take, and the response is an advised action. But there's also other ways you could do this. You could take essentially your value function. It's part of what you're learning through the policy exercise is what do we as agents value? What do I think is a good idea? And that's also something you can share. But as I said, the things you have to worry about are computational load in terms of if I give you this advice, how much effort is it taking for me to figure out what to give? How much effort is it taking for you to understand what it is that I gave you? How much of the link bandwidth are we actually using up while we're exchanging all this data back and forth? And then privacy. And so, again, the framework we're using is along the lines of teacher-student. You've sort of seen me talk about this before. So the student has to figure out when to ask and then also what to ask. And the teacher is then figuring out how to respond in terms of, and that's essentially what the policy ends up being. So give you a sense of sort of, what do things look like in the end. This is sort of a typical graph that we would show, well, at least in a theoretical paper. So high here is good, and so you basically want to be up here. You'd love to be able to do great performance with almost no training, right? That's not going to happen. You're going to have to take some training. What we have here is two sets of colors. There's the lower set, the orange and the red. This is using one very sort of, it's a discrete, very primitive, very sort of large-scale representation of the world from the discrete perspective. It's very fine, so it's a great discrete representation, but it's very big. The result is the learning process is quite slow. And you see that by the fact that you're getting performance is going up, but it's taking an awful long time to get there. Okay, it'll get there eventually, but it's just really super slow. Okay, so that's the discrete representation. You can also go to a continuous representation. I showed that picture before, and if you have a good representational tool, it can now capture the behavior in a much better fashion, and so you don't have to take as long in terms of learning, and you see that through the performance is getting much better, much more quickly as a function of training episode. But again, we're showing 4 lines here. So the sort of from this group to that group is the delta associated with the representation. If you change the representation from something that's crummy to something that's good, you can get much better performance. But the point here was to show that from green to blue and from red to orange is actually the delta you get from teaching. And so the piece that we're adding in here is, and these acronyms just are, if you look at the papers, you'll sort of see what these are. It doesn't matter a whole lot. It's just that these are non-teaching, these are teaching. And so now you're in a situation where both in terms of the ultimate sort of performance numbers up here are a little bit better in terms of the blue over green, but we also talk about the area under the curve. It's essentially how fast is this thing rising? And the point is that it's getting better through teaching. But again, that was sort of notionally what we expected at the beginning, right? That if I'm able to ask for advice, and I have a teacher who's an expert or has learned how to do this well, and has also learned how to be a good teacher, then the advice I'm going to get is going to be good. I'm going to be able to perform well. I'm also going to be able to learn well. And this is about how well you've learned, not how well you're actually able to perform the thing you asked about. So it's a true measure of the learning performance of these systems. And so this type of graph is the one that sort of captures the notion that learning, the sort of learning to be both a student and learning to teach are demonstrably improving the performance of the system from the baseline of just, as a robot, just wandering around exploring, okay? So we showed this in terms of these, and again, I apologize for sort of how boring some of these tables are, but this is sort of academically what you have to show. You have to hit people over the head with the fact that anything you could possibly think of, we tried, okay? And if you don't do everything they could possibly think of, the reviewer simply says, well, you didn't think of this. And so the only way to defeat that is to do absolutely everything. There are 2 sets here. One is the first table I showed you was us taking our algorithm, every possible reward that anyone's ever, I wouldn't say every, but the top ones, the ones that people like. This is the other path through all this, which is, well, what about all the heuristics that exist? People say, well, you know, you should try this kind of teaching, this kind of teaching. So this is against all the heuristics. And what's interesting about this is some of these heuristics basically get 0, right? They get no performance whatsoever, in part because there's just so much noise in this problem, they really don't know how to even get off the ground and get running. And our technique ends up down here with the kinds of numbers you saw before, okay? So again, could be better, but still amazing performance improvement over the heuristics that people have from before. And so this is a dramatic improvement over what we had. So this isn't exactly the same thing, but I wanted to show you that we're not just a theory group that sits around running algorithms on Amazon Web. We actually have a lab that sits right next to where my students are. And I showed the robot driving around before. We actually have a nice place to fly helicopters around. These are the quad rotors. It's actually a big enough lab that I can't take a picture with one video camera. So this is actually the two sides of the lab sitting side by side. This is the left side, this is west, this is east. They are actually overlapping in what they're showing. It just happens to look like it's two separate rooms, but they're not. And notionally what these robots are figuring out, and a slightly different problem that I just described, but what they're working on is how to jointly push a gray bubble across the room to a target location. So again, you can't see the bubble in real life, but as far as they're concerned, it exists. And so that gray thing exists in their world, they're just trying to push it over. And so part of what they're trying to learn here is the physics of how to move that thing around and how to actually move things together. And so this is something that neither one of those robots can actually do on their own. They actually have to learn to behave as a team. We're actually now swapping the robots around. This one does have a bit of a hiccup, but it recovers from it, and then they actually start working together. What's interesting here is now you have a team. The blue guys have figured out how to go to the east or go to the right. The red guys have figured out how to go to the left, but now they're in mixed teams. And now they actually have to train each other on how to be a good leftward team or a good rightward team. So this is that same type of sharing I described before, where basically you have red and blue now have to work together to become smarter at how to move to the left, even though red can't do it on its own and blue doesn't know how to do this, right? Because blue has learned how to go to the right and now it's being put on the left-hand side of the room and actually has to go to the left. And so basically red and blue now through the learning exercise, red is the teacher, blue would be the student, and that you'd be then in an exercise where they'd actually be sharing information on how to actually do this and actually move things around, okay? So those are the types of experiments we'll be doing. So again, just to summarize some of the contributions for the work, it's sort of a big picture problem. We're thinking about how to do multi-agent RL. The framework we've been taking is not just learning how to communicate, which is what some people have been doing in this work, where you have agents that they have knowledge and they're trying to exchange it. We're actually learning how to teach, right? So we actually have teacher agents, student agents, and policies, and they're actually learning how to be teachers and students in this framework. We've done it in the context of both the discrete, which is the tile coding, and the continuous, which is the deep neural nets, and basically now able to handle both discrete and continuous domains. The result ultimately ends up being a hierarchical representation. There's value in the discrete, there's value in the continuous, and when they're both valuable, you get the synergistic sort of combination of the two in a hierarchy, and that's where the 8 showed up in some of the algorithms I described before. We've handled the teacher credit assignment, one of the main issues. There's still improvements could be made, but I think we've taken big strides in addressing a key problem in this area. And what it leads to is sort of stable performance. And you don't see, by stability here, it's a situation where you actually forget things. You learn things and then forget them. In our technique, that doesn't happen. You have a much more stable learning behavior. And demonstrated performance is much better over different reward functions, but also over different, compared to the heuristics. The result then, I think, is an ability to share information between these robots, which will actually give us better performance. Ultimately, what we're looking for, and I apologize, there were a lot more graphics on this slide than there are now. There were some disagreements on who owned the copyright, and so they all got ripped out at the last moment, and so now this is just a bunch of words. But we've been thinking a lot, as you can imagine, about the self-driving cars. We've been thinking about multi-robot systems for delivery. There's also situations, I think, just in terms of manufacturing, where there's sort of a situation where, in a lot of these cases, there are things that agents learn through their interactions, which as a team they can also do sharing to improve performance between the agents themselves. And so I think that's many avenues for future implementation and application of this type of research. And so we're looking forward to the future. I do want to acknowledge my students, Don Key, Mike, and Samir. I spent a lot of time trying to get the slides finished while doing all the other stuff I asked them to do. And I want to acknowledge IBM and AWS for the support for the research. And with that, I will stop.